Awesome. All right. Well, hello, good morning, everybody. I hope that you are all having an excellent week. It's a little bit rainy today, but otherwise I think it's supposed to warm up, which is really, really nice. So as a reminder, we did not have a mini quiz yesterday. Our mini quiz will be due on Sunday on section 4.1, which we are continuing today. So we'd started with that last time, and we will continue with that today. So as a reminder, what we're looking at in 4.1 is thinking about local maximums and minimums. Last class, we spent time finding critical points, and now we are practicing figuring out how to identify those critical points. So I'm going to go ahead and switch over to the dot cam here. And so we're going to pick up where we left off last time. And what we were doing last time is we were looking at the graph of different functions to determine if our critical points were local maximums, local minimums, or neither. So that's what we're going to start with here today. So for examples 3 and 4, we're picking up right where we left off. These are two functions in which we determined the critical points last class. And again, we found those by setting the first derivative equal to 0. So I've listed the critical points that we found for each of these two examples, these two functions. And what we would like to do is we would like to try to graph these functions to see if we can determine if these points are local maximums, local minimums, or neither. So as a reminder, a local maximum is going to be a point in a small area where we are at the top of a hill. So we're going to have local maximums here and here. That's what we're looking for. And a local minimum is going to be at the bottom of a cup. And again, the lowest point in a small area. And the way that we've been finding these is by finding our critical points, because at these points, we have horizontal tangent lines. Okay, so we were able to determine by setting the first derivative equal to 0, or look at where the first derivative is undefined, the critical points for each of the functions we are discussing. So you can definitely look back at your notes if you want a refresher. But what we're trying to do in example 3 and 4 is seeing if we can graph these functions to determine if we can figure out if these things are maximums, minimums, or neither. Okay, so I'd like you to take 2 minutes, try to graph these. If you are not able to find a graph that tells you the information you're looking for, that is also interesting information we may be able to use. Okay, so again, take 2-3 minutes. If you have a graphing calculator, that'll be the easiest. You can do it on your phone if you have a phone, or you can plot some points out to see if you can determine, again, if at 0, 4, and 2, if this has a local maximum or neither, and then down here, 0, 1, and 3/7, if this function has a local maximum or neither. Okay, so try that out, and we'll go through it together in about 2 minutes. Okay, take about 30 more seconds. Okay, so what you may have noticed for these two functions is that these two functions are a bit finicky. They're a little bit hard to work with. You have to do a lot of zooming and moving around to figure out what the picture is going to look like, which is not the case with the two that we looked at last class. So the ones we looked at last class were polynomial functions that were a little more straightforward. So they're a bit easier to graph. And so I want to remind you that this is one of 3 tests that we can use to classify. So if you're having trouble getting a function graphed, we can certainly use one of the other tests that we'll learn later today. So when you graph x squared over x minus 2, we get something that looks something like this, right? So we have an asymptote at 2, and we have this hill and this u on either side. And so what that tells me, when I'm looking at what's happening at 0, I can see that it comes up and then it goes down. So remember, if you go from increasing to decreasing, right, that creates the hill, and that makes this critical point a local maximum. So 0 will be a local max. Now at 2, we see that we have an asymptote, right? So we have something that shoots down to infinity and goes way up to positive infinity from the right. So that means that here at 2, that's a case where we're going to have neither. That doesn't create a max or a min. We have a discontinuity there. And then at 4, this graph comes down, and then it turns around and starts going back up. So if we go from decreasing to increasing, that makes the point at 4 a local min. Okay. So again, we're trying to use the picture to help us understand what's happening at these critical points. Now, for example 4, I did this one on my calculator so I could show you guys. Now, if you plug this in, you may have found that it's a bit finicky. So here we have x cubed times 1 minus x to the 4th is our function. And we're really interested in what's happening at 0, 1, and 3/7. In order for me to have a picture that made any sense, I had to make the values on my window really, really small. So I see that my x values, 0, 3/7, and 1, don't go very far on the x-axis. So I made my minimum x -1 and my x max 2. So I'm just looking between -1 and 2, which is where these all fall. And then for my y scale, I needed to make this -0.1 and +0.1 just to be able to see what was happening at those points, because otherwise it looked flat. And so here, when I zoomed in that closely, this is what it looks like. And so here, what it appears to be happening, you know, for me, this little mark right here, that's the 1. So 1 looks like a minimum, 3/7 looks like the maximum, and 0 looks like it's going to be a neither. It looks like a weird flat spot. So that is sort of the conclusion I'm getting from this picture. But because it's so finicky, I'm not entirely sure. Fortunately, we are going to look at this with the other tests and we can confirm our suspicions. But again, I had to do a lot of zooming and rearranging. So sometimes graphing is not the best way to approach it. And so we'll sort of talk about that when we talk about the other tests. So for now, I'm saying that I think 0 is neither, because I think it's a weird flat spot. I was increasing and then increasing, right? But 3/7, which is right here, I'm increasing then decreasing. So I think that 3/7 is a local max. And then I'm decreasing and then increasing around 1. So right now I think 1 is going to be a local minimum. Okay, so if you are trying to use a graph in order to classify critical points and you can't quite get it to zoom in enough, or you can't tell what's going on, that's a good indicator that you need to use one of the other 2 tests. Okay, so let's do the next example. Here, where again, we're going to think about how we can find critical points based on our rules. And the rules say that if your function goes from increasing to decreasing, that's when we had the local max. Decreasing to increasing is when we had the local min. So we want to use that to talk about what's happening on this table. So suppose that we know that f of x and f prime of x are continuous functions that are differentiable. Additionally, suppose we know that f of x has a critical point at 5 and at 11. So we know where the critical points are. Just going to mark that on here. So 5 is going to be right about here, right between 4 and 6, and 11 will be between 10 and 12. Use the table of values below to determine if these critical points are likely to be local maximums or local minimums. Okay, so I'd like you to take a minute. I'd like you to think about what we know about the behavior of f of x and see if you can figure out if these are going to be local maxes and mins. So jot down your thoughts and then we'll go through it in a minute. Okay, so how do we use this table of values to figure out what's going on with these critical points? So what we want to know is if the original function is increasing or decreasing around the critical points. So when we look at the values here, we have 4, 8, 10. So these are increasing as we approach 5. Now after 5, we have 8, 5, 2. So those are decreasing. So if we have a function that's going from increasing to decreasing, that means it's going up and then coming down. That means that x equals 5 is most likely to be a local maximum. Okay. Similarly, if we look at what's happening at 11, so before 11, we have 8, 5, 2, so we're decreasing. And then to the right, we have 7 and then 10. So that's increasing. So if our function goes from decreasing to increasing, that creates that U pattern, which tells us that this is going to be a local minimum. So if we know where the critical points are on a table, we can look at the behavior of the function in terms of increasing and decreasing to figure out if that critical point is going to be a local max or a local min. Okay. So the key takeaway from the first test is mainly visual, right? We're looking for where things are increasing and decreasing, whether on a graph or on a table, to help us determine the shape of the function, which would then help us understand whether it's a local max or a local min. Okay, so now we're going to talk about the second test that we can do. And the second test is called the first derivative test, because we're going to be doing some analysis on the first derivative to help us understand the behavior of the original function. So let's go back to our example here. We have 4x cubed minus 6x squared minus 72x plus 12. So this was the first example we did under classifying critical points part 1. And so what we do when we find critical points is we find the first derivative in order to find our critical points. We've already done that part last class, but we're going to do it again here because we do need the first derivative for this to work. So when we take the derivative of 4x cubed, we get 12x squared minus 12x minus 72. And then the derivative of 12 is 0 because 12 is a constant. We then factored this. Okay. And when we factored it, we had 12 times x minus 3 times x plus 2. And that factoring helped us find the critical points by setting this equal to 0. And we found critical points at x equals 3 and x equals -2. Okay, So how do we do the first derivative test? What's sort of the process for this? So what we want to do is we want to take our first derivative and we want to factor it, if we can, into pieces, because that's going to help us with our testing. We are going to take our critical points, okay, and we're going to use those to create intervals on a first derivative number line, okay? Let's go to the next page and talk about what that might look like. So again, our critical points, we had x equals 3, x equals -2, and our factored derivative was 12 times x minus 3 times x plus 2. Okay, so we want to take our critical points and we want to divide them onto a number line of the first derivative. So what does that mean? That means that we are going to take a line like this. We're going to label it f prime of x. We're interested in the first derivative, and we are going to put our critical points onto this line. Okay, just like you would a number line, we want -2 to come first and 3 to come second, because in a number line, we go in increasing order. Because what happens is that critical points divide the domain of the original function into intervals. And so what we're going to do is we are going to use the sign of the first derivative to help us understand whether we have local maximums or local minimums. So what does that look like? So we know that the derivative is 0 at our critical points. So at -2 and at 3, the value of the first derivative is 0. If we want to know what's happening on our intervals, we need to pick some points to test. So we want to pick these points to be as easy to test as possible. Okay, so here when I pick something for this first interval, which is -∞ to -2, I'm going to pick -3. That's going to be an easy point to test. It's a whole number. That for me is going to be the easiest point, but you can pick anything on this interval. So you could pick -4, -5, -100, any of that's fine. And so what we want to do is we want to go up to our first derivative. If you have it factored, it does make it a little bit easier. And we want to know what is the sign of the first derivative when you plug in your test point. Okay, so if I'm plugging in a -3, I look at each factor. The 12 will always be positive. Now, if I plug in a -3 into this factor in the middle, I have -3 minus 3. That's going to give me something that is negative. And then if I plug in a -3 plus 2, I also get something that is negative. Okay, so positive times negative gives me an interval that is positive. So that's what I'm looking for. Is my interval positive or negative? So we're going to do this for this interval and this interval. So between -2 and 3, I'm going to pick 0. 0 is something easy to plug in. So here 12 will be positive. If I plug in a 0, 0 minus 3, that's negative. And if I plug in a 0 here, 0 plus 2, that's something that's positive. So positive times negative times positive gives me something negative. And then finally, I'm going to pick a test point over to the right of 3. I'm going to pick the value of 4. Again, I can pick any number bigger than 3, but pick one that's convenient. So if I pick 4, 12 is positive. 4 minus 3, that's positive 1. 4 plus 2 is positive 6. So positive times positive times positive, right, gives me positive. You can plug this into your calculator and get the number if you'd rather do that, but the key takeaway information is whether that number is positive or negative. Okay, so why did I want to do this? Well, this goes back to the relationships that we talked about back in chapter 2. If your first derivative is positive, that tells you that the original function is increasing. If your first derivative is negative, it tells you that your original function is decreasing. So this is helping us again understand what the graph looks like. If we go from positive to negative on the derivative, that means we go from increasing to decreasing on the original function. And if we go from increasing to decreasing, we know that that creates a local maximum. So here, that's going to help tell us that -2 is a local maximum, again, because on the original function, we are going to be increasing to the left of -2 because the derivative is positive. We are going to be decreasing to the right of -2 because the derivative is negative. So if we go from increasing to decreasing, that creates the local max. Similarly, we were decreasing to the left of 3, and now we're going to be increasing to the right of 3. So if we go from decreasing to increasing, this creates a local minimum. Okay, so really taking the time to understand the relationship between the sign of the derivative and the behavior of the original function is important analysis that we need to do. This is the critical thinking component and not necessarily computation. So you want to make sure you really understand these relationships as you practice and learn these different rules. So the second set of rules that we get, so classifying critical points here, we have if the derivative changes from positive to negative around P, so P is your critical point, so positive to negative, then that point is a local maximum. If the derivative changes from negative to positive around P, so negative to positive, then that creates a local minimum. And if the sign does not change around P, then it is neither. So if we had like positive, positive, then that critical point is not a local max or a local min. Okay, so what we're going to do is we're going to practice this test now with all the functions we've been looking at from before. So we know the critical points from last class, but we want to use a different test. So, it's going to be helpful to sort of find the first derivative for all of these functions. I will just remind you what the critical points are since we already walked through them. If you'd like to do them again, that's fine. For this one, we'd found that x equals -1. That's the critical point we're interested in. And for this one, 2x cubed minus 3x squared minus 36x plus 14, we had found that the critical points were x equals 3, x equals -2. Okay, so for both of these, what I would like you to do is I would like you to find the first derivative of the function and then set up a number line like we did here to determine the sign of the derivative on the intervals that are created by putting the critical points on that number line. Okay, so again, you're going to find the first derivative because that's going to help you test. And then you're going to have a number line where on this one, you're going to put -1. So you're going to have to test something to the left of -1 and to the right of -1 to see if we're changing from positive to negative, negative to positive, or not changing at all. And once you've seen how it changes, you can use these 3 statements to make your determination. And then you'll do the same thing for example 2, right? You're going to find the first derivative. You're going to put our critical points on a number line. You're going to find the sign on that interval, and you'll use that to classify. So I'm going to give you about 3.5 minutes to try these out. If you have extra time, you can confirm our critical points, right? Check them, do the algebra again, just for good practice. But take about 3 minutes, and then we'll go through them together. Okay, I'm going to move this down just so you can see the number line that we did before, as well as the rules, and you can see the function we're working with and these critical points. Okay, try it out, and we'll go through it together soon. Okay, take about 30 more seconds. Okay. So again, our process is that we were finding the first derivative. We were using that to find the critical point. That's always step one, but we'd already done this one last time. If you set this equal to 0, you find that x equals -1. Now, the second step is the classification. So we're using the first derivative test right now and practicing that. And the first derivative test says we're going to put our critical points on a number line to create intervals. Since there's only one critical point here, it creates two intervals, the left and the right. We want to pick a test point on each side of our critical point. So to the left of -1, I can pick -2. And what I want to do is I want to take -2, plug it into my first derivative, and determine if the result is positive or negative. So if I plug in a -2 here, I have 6 times -2, which is -12, plus 6 is -6. So this is negative. Okay. I also want to test something to the right of -1. And again, you can pick any number. So you want to pick something that's going to be convenient. So I'm going to pick 0. So here, when I plug in a 0, I get 0 plus 6. That gives me something positive. Okay. So if our function goes from negative to positive, if our derivative changes in that way, that means that f of x went from decreasing to increasing. And if the function goes from decreasing to increasing, we know that that creates a local minimum. That's the same thing that we have up here. If we go from negative to positive, then our critical point, which was -1, is a local minimum. Okay. So again, we're really interested in how this changes. And if you have your notes from last class, when we graphed this function, we found that it was a local minimum. It looks something like, if we put this here, right? It ended up looking like this when we graphed 3x squared plus 6x plus 1. You know, over here at -1, we saw that it was a local minimum. So this is going to agree with the other tests that we did. You're not going to get different conclusions. Okay. So now let's look at the next one. So again, we have our first derivative. If you factor it out, it looks like this. We want to take our critical points, which we get from setting the first derivative equal to 0. And we use those to divide up our number line. And then we want to test points on each interval. So if we test something like -3, right, we have something positive, negative, negative. The negatives cancel. We end up with a positive result. Something between -2 and 3, we can do 0. So positive, negative, positive. That's going to give us something negative. And then something bigger than 3, I'm going to pick 4. We get positive, positive, positive. So again, what that tells me, if at my critical point, which is -2, I go from positive to negative, I come up here, positive to negative, that gives me a local maximum at -2. So we'll just draw a little arrow here. This is a local max. And then over here, if we go from negative to positive, that's going to make 3 a local min. Okay, and again, that agrees with the work that we were doing last time. Let's see, I don't know if I have the picture still. When we graphed this out, right, we found the same exact thing, that 3 was a local min and -2 was a local max. Okay, so this is sort of the process that we're using. We're thinking about the sign of the first derivative around the critical points to help us classify. Okay. So we won't do the graph one yet. For examples 3 and 4, we want to try this again. And I am going to go ahead again and tell you what we found these to be. These are the first two we graphed. So we actually have a good guess from the beginning of class today. So for x squared over x minus 2, our critical points for x equals 0, x equals 4, and x equals 2. And as a reminder, when we did our first derivative, we had to do a quotient rule and we had to simplify it. And so our simplified first derivative was x squared minus 4x all over x minus 2 squared. So you can certainly look back in your notes at how we got that, or you can use the quotient rule to double check, but that's what we found last class. So we want to use that with a number line to help us determine how to classify these points. So again, we're going to throw them all on the number line here. So 0, 2, and 4. And then we have to test points in between. Okay, we're going to do the same thing with our second function here. And again, we already found these critical points earlier in an earlier example. So we had x equals 0, x equals 3/7, and x equals 1. And if you remember from last class, we did spend quite a bit of time factoring the first derivative. And so the factored form of this was x squared, 1 minus x cubed, 3 minus 7x. So that's what our factored first derivative looked like. We had to do the product rule to get the first derivative, and then we sort of factored things out to see, what would shake out. And that's what our factored first derivative looks like. So what I'd like you to do again is I'd like you to use this first derivative test to classify these critical points. So we have 0, 3/7, and 1. This one's a little tricky. Make sure that you're picking a number between 0 and 3/7, or between 3/7 and 1. If you're not sure, you can definitely turn things into decimals to give yourself the best opportunity to figure out what those points may be. But try them out with this method, see what you can shake out. I'm going to give you about 3.5 minutes. Try it out, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So we already talked about how these particular functions are more complicated to find critical points because we're using things like quotient rules and product rules. But they're also a little more tricky when we're plugging things in to use this test. Now, at the beginning of class today, we did graph both of these. So we do have an idea of what's happening. So for example 3, we know that there's an asymptote at 2. So we know there's something weird going on there. How do we go ahead and use this first derivative test to classify and look at what's going on? So again, we lay out our critical points on a number line in increasing order. This creates intervals, okay, around the critical points. We need to find the sign of the intervals. So one thing that I notice on my derivative function is that I have a numerator and a denominator, right? But my denominator is something squared, which means my denominator is always going to be positive, right? It doesn't matter what numbers I plug in here, we're going to get something positive because I'm not plugging in 2 because that's one of my critical points, right? We're plugging in things around 2. So since the denominator is always going to be positive, I really only have to plug my test points into the numerator. Okay, so starting here, I'm going to pick something to the left of 0. I'm trying to make my life as easy as possible, so I'm going to pick -1. So when I plug a -1 into the numerator, I have -1 squared, which is +1, minus 4 times -1. Well, the minus and the negative are going to cancel, and that's going to give me something positive. Okay. Now I want to pick something between 0 and 2, so I'm going to pick +1. If I plug in a +1, I end up with 1 minus 4 on the top, which is -3. So that's going to be something negative. If I pick something between 2 and 4, I'm going to pick 3, just because that's easy. 3 squared is 9 minus 12. 9 minus 12 is a negative number. So that's negative. And then I'm going to pick something bigger than 4. So say 5. So 5 squared is 25 minus 20. 25 minus 20 is positive. So what does that tell me? That tells me that at 0, my derivative is changing from positive to negative, so increasing to decreasing, which tells me that my critical point of 0, just in another color, is a local max, because we went from positive to negative. At 2, I see we go from negative to negative. So that means the sign did not change. And so I don't have a local max or a local min. And we know from the graph that's because I actually have an asymptote. So I don't have either. It's just sort of a weird discontinuous spot. And I can identify that because the sign does not change around 2. At 4, I'm going from negative to positive. So negative means I'm decreasing, and positive means I'm increasing on the original function. So decreasing to increasing means that 4 is going to be a local minimum. Okay, so that's how we're plugging things into the derivative on this one. Again, this, goes with what we said before from our graph, that 0 is a local max, that 4 is a local min, and that 2 was neither. Just as a reminder, the picture looked like this, right? And so that agrees with the picture. So since we had that information from the graph, we don't necessarily need to use the first derivative test, but if we do both and they agree, that's a good sign for us. Okay, so now let's look at the next one. So here the numbers are a little tricky because they're small. There was a lot of algebra in getting our first derivative. Okay, but now we can sort of test things to see, are they going to be positive, negative, 0, and what's going on here. We said from the picture before, which I can show you one more time. You know, the picture that we had looked like this. It was a little weird, a little goofy. So something goofy is going on at 0, right? Because it's kind of increasing and then increasing again. So we're expecting something weird at 0, probably a local max at 3/7 and a local min at 1. So let's see if that shakes out with our analysis here. Okay, so we're going to pick something slightly to the left of 0. So we can pick -1. Again, you can pick any number to the left of 0 since that goes on forever. So -1, if we plug in a -1 into x squared, that's going to be positive. If we plug in a -1 into the second factor, we have 1 minus -1. So minus and the negative are going to cancel, and that'll be positive 2 cubed. So that's going to be positive. And then a -1 here will make this term positive. We end up with 3 plus 7. So that's positive as well. So positive times positive times positive gives me something positive. Now, here's where we need to be a little careful about our test points, right? So depending on how comfortable you are with fractions, we need to figure out something between 0 and 3/7, okay? For me, the way that I approach this, I know that 3/7, if I turn that into a decimal, is about 0.4. So I like to turn things into decimals so I can pick out what I want to test. So this is about 0.42, okay? So I'm going to pick something between 0 and 0.4 that is convenient. So I'm thinking 0.25, right? I like 1/4 as a contender here. You can do it as a decimal or a fraction, whichever you prefer, but just make sure you're picking something between 0 and 3/7. It's really easy to accidentally pick something outside of that interval. So 1/4 or 0.25. We know that if you square anything, it's going to be positive. So this is going to be positive no matter what. 1 minus 1/4, that's something positive cubed is positive. And now here is where I have to be a little careful. So 3 minus 7 times 1/4. 7 times 1/4 or 7/4 is going to be about 1 3/4. So this is also going to be a positive number. If you're not super comfortable with fractions, just put this into your calculator, right? 3 minus 7 times 1/4, and it'll tell you if it's positive or negative. So here, right, we get something positive. Then we want to test something between 3/7 and 1. And again, this is about 0.4. So I'm going to pick half as my test point, which is about 0.5. So here, if I plug in a 0.5, 0.5 squared is positive. Here, 1 minus 0.5, that's positive. So if I cube it, it's positive. Here, 0.5. So half of 7 is 3.5. So 3 minus 3.5 will give me something negative. So positive times negative is negative. And then finally, I need to test something slightly bigger than 1. So I'll pick 2. So 2 squared is positive. 1 minus 2 cubed. So 1 minus 2 is -1. -1 cubed is negative. 3 minus 14, that's also going to be negative. So I have positive times negative times negative. The negatives will cancel, and I will get something positive. Now, I will be very frank that the algebra on this entire problem is what makes this complicated. So again, the algebra is really coming back in this chapter. So hopefully, you're comfortable with fractions and factoring and those sorts of things. But if not, definitely come to Drop and Help so we can go over more problems with you. So now this means that 0, positive to positive, that makes 0 neither, which is what we were expecting. It's that weird flat spot. 3/7 goes from positive to negative, so increasing to decreasing. That's going to make that a local max. And then finally, at 1, we go from negative to positive, so decreasing to increasing, which makes that a local minimum. Okay, now, depending on your algebra, you may or may not prefer the first derivative test. And depending on what you have, you may not need the first derivative test, but there are definitely problems where you have to use the first derivative test. So there are problems where you are just given the first derivative and you are told to find, the local maxes and mins of the original function. So your steps would be to set it equal to 0 to find the critical points. And then you would have to use this test to classify them if you don't actually have the original function. If you have the original function, you can certainly graph it. But if you don't, then you don't have the ability to use that first test we did. So even if this is not your preferred method of classification, you still need to make sure you know how to use all three tests, okay? So the next two examples go back to the graph that we were looking at for critical points and the table. The graph is on the next page. So the idea is that we have a graph of the first derivative, and we want to use that to determine where f of x has local maximums or minimums on the interval -2 to 8. So we already used this graph to find the critical points in the last class, if you remember. So this was our first derivative. And we said our critical points are where the first derivative equals 0. So here, here, and here. But now we want to use this graph to determine if these critical points are local maximums, local minimums, or neither. So we're using the first derivative test to think about how the derivative changes, right? Because if it changes from positive to negative, that tells you something. If it changes from negative to positive, that tells you something. And if it doesn't change, that also tells you something. So I want you to take a minute to think about those three rules of the first derivative test and how we might be able to use them to classify these three critical points where we cross through the x-axis. Okay, so take a minute, jot down what you think, and then we'll go through it together. Okay, so when you have a graph of the derivative and you are using that to talk about the local maximums and minimums of the original function, the first step is to identify where the first derivative equals 0. So again, that is where we cross through the x-axis. We see that this happens 3 times. The second step is to determine how it crosses through. So we read graphs from left to right. So what we see here is that we start off positive because we're above the x-axis. We go through the critical point, and then we change to negative. So if your first derivative goes from positive to negative, that makes your critical point a local maximum. Okay. Now we go over to our next critical point. We see that to the left, we are negative because we are below the x-axis. And then we change to positive. And so if your first derivative changes from negative to positive, your critical point is going to be a local minimum. And then finally, our last critical point over here, again, we see what's going on to the left and to the right of our critical point. To the left, we are positive because we are above. To the right, we are negative because we are below. If you go from positive to negative, you have a local maximum. Okay, and again, you have these local maximums and minimums on the original function. We don't have that graph. We don't have that function. We just know that this is where they are on that picture. Okay, so similarly, right, if we're thinking about this on a table, last class we talked about where the critical points are. We said that there's one at 6, right? Because again, this is a table of the derivative. So when the derivative equals 0, you have a critical point. So that happens at x equals 6. But then we also had one between 10 and 12, right? Because we saw that our derivative went from positive to negative, and we know that in order for this to change signs, it had to go through 0. So there's a critical point at 6 and one between 10 and 12. So now we want to use our first derivative test to determine whether these critical points are local maxes, local mins, or neither. So again, we're looking at how the sign of the first derivative changes. So for this first critical point, we see that it was negative to the left of 6 and positive to the right. So if your derivative goes from negative to positive, that makes your critical point a local minimum. Over here, we know that our critical point is between 10 and 12, and we see that the values of the derivative go from positive to negative. So this critical point between 10 and 12 has to be a local maximum, okay? So the key takeaway here for our second classification test is that we need to understand how the sign of the derivative changes. So once we know how it changes around a critical point, positive to negative or negative to positive, or doesn't change, that's what tells us if it's a local max, local min, or neither. So if you are presented with information about the first derivative, that is when it's appropriate to use the first derivative test. Or if you are able to find the first derivative, you can then also use the first derivative test. So that's the second test. The third and final test of classifying critical points is going to be looking at the second derivative. So just as a reminder, the second derivative of a function tells us about the concavity of the function. We learned that back in 2.5. So we're bringing back this idea of concavity because if something is concave up, it creates a natural minimum. And if it's concave down, it creates a natural maximum. So we can also use this to help us understand what's happening at our critical points. So how does this work? So if we have a function 4x cubed minus 6x squared minus 72x plus 12, just like before, we would start by finding the first derivative so that we could find our critical points, which we've already done. So I'm going to do this quickly. So 12x squared minus 12x minus 72. We factored that out. We got x minus 3, x plus 2, set it equal to 0. We got our critical points. We have x equals 3 and x equals negative 2, right? So that would sort of be the first steps to find your critical points. To do the second derivative test, we then would find the second derivative of our function. So here we want to go back to the unfactored version to find the second derivative. So here 12x squared, the 2 comes down and we have 24x minus the derivative of 12x is 12 and the derivative of 72 is 0. So what we want to do is we want to plug our critical points into the second derivative to determine the shape of the graph. Because if we know the shape of the graph, we will know if the critical point is a minimum or a maximum based on the concavity. So what does that look like? So let's say we take the point 3 first. We literally plug it in. So 24 times 3 minus 12, that gives us 60, okay? The 60 itself is not what's important. What's important is the sign, okay? The sign of 60 is positive. If the second derivative is positive at a point, so at the point 3, that makes it concave up, okay? So hopefully you remember that from chapter 2. So since it's concave up, that means that 3 is a local minimum. Now, we got that with our first derivative test. We got that with our graph. So this is just, confirming what we already know. Then we also want to plug in negative 2. So we have 24 times negative 2 minus 12. That gives us negative 60. And again, what we're interested in is the sign. So we're interested in the negative. So since it's negative, that means it's concave down. When your second derivative is negative, you get a function that is concave down, which means at negative 2, the function is concave down, which makes 2 a local maximum. Okay, so we add to our list now our third test that says if the second derivative is positive at our critical point P, the function f of x is concave up, and it makes our critical point a local minimum. If the second derivative is negative at P, the original function's concave down, so it makes our critical point here a local maximum. So we are able to use the second derivative to again classify our critical points. Okay, so I want you to try this. Yeah, let's I want to make sure we get through a certain example. So let's just do this one. This one's pretty straightforward. We've done this one before, but do all the steps. Find the first derivative, use that to find the critical point, then find the second derivative and use the second derivative test to classify that critical point. Okay, so I'm going to give you about 2 minutes since we already know the critical point from before, but try it out, try out the second derivative test, write out all the steps, and then we will go through it together. Okay, take about 30 more seconds. Okay, so when we find the first derivative of this function, we get 6x plus 6. We would then set that equal to 0 to find our critical point. So our critical point is -1. We would then go ahead and find the second derivative of this function, which the derivative of 6x is 6, and the derivative of 6 is 0. You may notice that there's nowhere to plug in our critical point. That's okay. What that means is that this function is going to be concave up everywhere, right? So if you can't plug something in, that's because it's concave up everywhere, which we know is true because our picture, again, that we got for this looks like this. It's just a U shape. So that means it's concave up at -1. If it's concave up, that means that we have a local minimum. So even if you can't plug in your critical point, you can still use the second derivative test. The only time that we run into trouble is if the second derivative equals 0, which is not positive or negative, but that is a special case that we will learn how to deal with next week. Okay, so in general, this is what we are doing. We are finding the second derivative and plugging in our point to check if it's a local max or a local min. I'm going to skip the algebraic ones because I think you can try that on your own to find the second derivative. I will tell you the second derivative test really makes sense if you are given information about the second derivative or if you have polynomials. The harder the function gets to find the second derivative, the less likely you would want to rely on that. Okay, so we're going to jump to example 5. And if we have time, we'll also do 6. But 5 is sort of an analytical problem that is really good to sort of bring in all the tests that we've been talking about. And so I want to make sure we got to this, because this is the type of critical thinking and analysis that really pulls together all the things we've been talking about to make sure that we can understand it in sort of a bigger, broader way. So suppose that f of x is a continuous differentiable function and that we know the following information. So we know that f of 1 equals 10, f of 7 equals 1, f prime of 2 is 4, f prime of 4 equals 0, f prime of 9 equals 0, f prime of 12 equals 8, f double prime of 4 equals -4, and f double prime of 9 equals 3. So we want to use this information to determine where f of x, the original function, is likely to have any local maximums or minimums. Okay, so I want you to really think about this. I want you to see if you can figure it out. I'm going to give you 2 minutes to think about the tests, what we know about where local maximums and minimums are, how we might approach this. So take 2 minutes, see if you can really think about it, and then we will go through it together. Okay, take about 30 more seconds. Okay. So since we are trying to understand where we might have a local max or min on the original function, the first thing we need to do is figure out if we can identify critical points, because we know that maximums and minimums happen at critical points. So the first thing we're asking is, do we know of any places where the first derivative equals 0? Right? So that means we have to look at the derivative statements. There's 4 of them. And there's 2 places where we are told the derivative equals 0. Okay, this one happens at x equals 4, and this one happens at x equals 9. So we know we have critical points at 4 and at 9. So how do we classify critical points? The original function test requires that we know either a picture of the function or where it's increasing and decreasing. We don't have that information, so we're not going to be able to use the original function test, f of x. In order to be able to use the first derivative test, we would need to be able to put our critical points on a number line, so 4 and 9, and we would need to know the sign at 3 different places. So something to the left of 4, well, we know that, right? We know that to the left of 4, we could use 2, that's positive. We also know that f of 12 is 8, so it's also positive to the right of 9. Unfortunately, we don't have any information about what's happening between 4 and 9. So we can't actually use the first derivative test because we don't know if it's positive or negative, and that makes a difference. So that brings us to our second derivative test. If we know the sign of the second derivative, that will tell us the concavity and will help us know if it's a local max or a local min. So notice here that we know the sign of the second derivative at 4 is -4. Okay, so if the second derivative is negative, that makes the original function concave down, which makes 4 a local max. And the second derivative at 9 is +3. If it's positive, you are concave up, which makes 9 a local minimum. Okay, so there is a lot of information to synthesize in this problem, but what it's meant to do is to help you sort of sort out what information is relevant and useful versus what information is sort of not that helpful, right? And you do really need to think about how to apply each part of this to come to these conclusions. But the first thing, whenever you are talking about local maximums and minimums, should always be critical points. You have to start and go through critical points and then build from there. Okay. Now I'd like to quickly talk about number 6, because again, this is sort of a more analytical problem that I think is really good to help us understand what these tests are telling us. So it says, suppose that f of x equals ax squared plus bx minus c, where a, b, and c are non-zero constants. So we looked at this problem before to find critical points. And the question is, what has to be true about a for this function to have a local minimum? Okay, so as a reminder, when we were talking about critical points, we found the first derivative, which was 2ax plus b. When we solved for x, we got -b over 2a. That was our critical point. Okay. We are not able to graph the original function because we don't have values for a, b, and c. We really are going to have a hard time using the first derivative test because how are we going to pick points on either side of this when we don't know the values of a and b, right? And so the last resort here is to examine what the second derivative might tell us. So when we take the second derivative of this function, we're taking the derivative of 2ax plus b. 2a is our constant, so the derivative of 2ax is 2a, and the derivative of b is 0 because it's a constant by itself. If we want this function to have a local minimum, okay, that means that we want our function to be concave up, which tells me that my second derivative has to be positive, okay? In order for the original function to be concave up, the second derivative must be positive, which means that 2a has to be greater than 0. Since 2 is already positive, that means that the condition that I have to put on a in order for me to have a local minimum is that a has to be positive. A has to be greater than 0. If a is greater than 0, the second derivative is positive. If the second derivative is positive, the original function's concave up. And if the original function's concave up, then our critical point is going to be a local minimum. Okay, so again, there's a lot of relationships that we are balancing when we use these 3 tests. The better you understand the relationship between the behavior of the original function, the first derivative, and the second derivative from chapter 2, the easier it is to do the type of analysis we need within these tests. Okay, so we will stop here. Hopefully you'll be able to do all the homework here, but again, definitely stop by Drop In Help if you have questions about any of the algebra or analysis we're doing. And then on Tuesday of next week, we will talk about section 4.2, which is called inflection points. Okay, have a great rest of your day and a great weekend.